Hello and welcome to today's lecture on minimizing switched capacitance. In the last 4 lectures, we have discussed various techniques of supply voltage scaling for minimizing power dissipation. We have discussed static voltage scaling, multi-level voltage scaling, and also we have discussed dynamic, frequency and voltage scaling. Now, we shall switch to a new topic, that is minimizing switched capacitance. And as you know, based on our study of sources of power dissipation, we identified 4 degrees of freedom, that is supply voltage, physical capacitance, switching activity and threshold voltage, which can be used to reduce power dissipation in CMOS circuits. And based on the various techniques that we shall be discussing, they can be categorized into 3 types, as I mentioned. First one was supply voltage scaling, second one is minimizing switched capacitance, which I shall discuss, which I shall start our discussion on this topic today, and after that we shall discuss minimizing leakage power. We have already seen the switching power dissipation expression, that is alpha 0 C L V D D square F plus summation of alpha I C I V I V D D F. This is the switching power dissipation that take place in CMOS circuits, and essentially this power dissipation occurs because of charging and discharging of capacitors. Now, the switching power dissipation can be minimized by minimizing capacitance and or switching activity. Of course, you can minimize by using supply voltage, which we have already discussed, but apart from minimizing power dissipation by scaling down the supply voltage, another technique is to reduce the power dissipation by reducing the switched capacitance. By switched capacitance, I mean which is a product of switching activity and capacitance. So, essentially alpha VDD alpha CL, that means alpha CL represents the switched capacitance. Either we shall minimize switching activity alpha or C or together. So, we shall discuss various techniques of minimizing switched capacitance. You can see here is a big list. First one is hardware software trade off, then bus encoding, use of number systems, then there are various architecture level optimization techniques, then glitching power minimization techniques, clock gating, state encoding, logic styles. So, today we shall start our discussion on hardware software trade off. What do we really mean by hardware software trade off? Whenever we start designing a system, first we identify which part to be implemented by hardware, and then that hardware part of the design will follow the flow of hardware design will take place. That means, the hardware design flow will be used to realize the hardware. Similarly, we identify which functions we can realize by software, and then there is a traditional software design flow. The software design will take place using that flow, and then of course, you have to do what is known as system integration. That means, you have to integrate hardware and software. Now, a very important step is identifying which part to be implemented by software, which part to be implemented by software. There is a trade off. So, the trade off is based on cost, performance, power dissipation and so on. So, let me illustrate with the help of an example, and this example is coming because same functionality can be either realized by hardware or by software or by a combination of both. That means, you will find that a particular piece of function, whether it is analog to digital conversion or compression or decompression or encryption or decryption, many such functions you will encounter in embedded systems or various other applications. These functions can be implemented either by hardware, fully by hardware, or by software, or a judicious combination of hardware and software. question is how to implement them efficiently. And obviously, whenever you implement it by hardware, it will be faster, and unfortunately it will be costlier, and more importantly it will consume more power. On the other hand, we know that whenever you go for software based approach, it is cheaper to implement because you do not require any additional hardware. However, a software based approach will be slower in performance, but most important is it will consume much less power. Let me illustrate with the help of a very simple example. Suppose you have to implement an 8-bit analog to digital converter in the context of a microcontroller based application, where maybe you have to sense temperature, ambient temperature or temperature of a water bath or whatever it may be. So, you have to convert an analog voltage to a digital one. This is a very common requirement in almost many embedded applications. How do you implement the analog to digital converter? The first approach is to implement it with the help of a pure hardware. That means, what you can do, you can use one ADC chip, analog to digital converter, then it can be interfaced to a microcontroller. So, here is your microcontroller, and of course, microcontroller interfacing can be done through the data bus. This is your data bus. So, say D0 to 7, because it is 8-bit AD converter. Then there will be 2 additional lines for handshaking, because the microcontroller will initiate send a signal to start conversion, and also there will be another line which is end of conversions. These are available in analog to digital converters, which these signals will go to port lines of a microcontroller, and then you will interface this ADC, and obviously there will be analog input here, and the analog to digital conversion can be done. So, this is the first approach. So, in this particular approach, we find that ADC function is implemented by hardware, and obviously you will require very few lines of software. That means, start conversion signal, for sending the start conversion signal, one signal, then one few lines of code, another few lines of code for monitoring to see when the end of conversion signal is coming, then another 1 or 2 line to read the data from the data bus. So, the software part is very simple here, but you are using a costly hardware, because this ADC is usually costly, and of course, it is fast and it consumes more power. Another implementation technique is, you can realize a analog to digital converter function with the help of a digital to analog converter. You can interface one digital to analog converter, and then of course, you will require some additional hardware, that is your comparator. So, this analog to digital, the digital to analog converter will receive input from the microcontroller, and the output of the DAC, which is an analog signal, will be applied to one input of the comparator, and another input you will apply the analog signal, analog input, and this will be going to one port line of the microcontroller. And of course, usually a pull up resistor is needed for interfacing it to microcontroller, because this comparator can be implemented by using say LM393 chip. So, this is how you can interface a digital to analog converter, then you will be applying the output of the ADC to a comparator, and comparator output is fed to microcontroller. Now, the question arises, how do you really implement the analog to digital converter operation? The analog to digital conversion function that is your successive approximation algorithm, can be realized in software. You can write a program, of course, the program will be little longer, and by that you can implement that successive approximation algorithm, and successive approximation algorithm will perform analog to digital conversion with the help of this digital to analog converter and comparator. So, in this particular case, you see the digital to analog converter is a much simplified, much simpler than analog to digital converter. For example, if the cost of the ADC is rupees 500, the cost of a DAC is rupees 50. So, order of magnitude difference in cost, not only order of magnitude difference in cost, order of magnitude difference in complexity. So, the power consumption of DAC is much less. However, here the operation will be slow. So, although it is cheaper to implement, for example, total cost of implementation will not exceed maybe 200 less than, it will be less than 200 rupees. On the other hand, the cost of ADC itself here will be rupees 500. So, it will be much cheaper to implement, however, it will be slower and power consumption will be less. So, less power consumption. So, we find that with the help of this simple example, we have seen the hardware software trade off. The analog to digital conversion operation can be either realized in hardware or it can be realized in software, and depending on your requirement. If you require very fast conversion, obviously you have to go for this particular choice. That means, you have to use this fast technique where you will be using analog to digital converter chip. However, in numerous applications, the conversion need not be very fast. For example, when you are monitoring the temperature of a water bath, or monitoring the temperature of geyser, or monitoring the temperature of a air conditioned room, in such cases the temperature does not change very quickly, and obviously you have the option of using slow analog to digital conversion, and in such a case you can use this second option, and whenever you use this second option, you have the benefit of cheap implementation and the power consumption is less. So, this is a very simple example by which I have illustrated the software hardware trade off. Now, let me go to a more complex application, more complex example, but very important example. Here we shall consider two different CPU architecture. One of them is superscalar architecture. All of you may not be familiar. So, I shall briefly explain what do you really mean by superscalar architecture. All the Intel processors, Pentium, starting from 386, 486 to Pentium, all of them are superscalar processors. What do you really mean by superscalar processor? Superscalar. As you know, the performance can be improved, performance of a processor can be improved by incorporating parallelism. So, in the beginning, say if you go back to the days of 8085, 8086, inside the CPU there was a single functional element. That means, there was only one ALU, arithmetical logic unit. But now, with the advancement of technology, it is possible to put more functionality in a single CPU. So, what was done? More than one functional elements were provided inside a CPU. So, normally say this is a CPU. Inside the CPU you can have several functional unit. One can perform floating point operation, one can perform fixed point operation, one can perform load and branch operation, like that. So, you can have several functional unit within a single processor, essentially to increase the throughput of the processor. That is the basic idea behind superscalar architecture. So, a superscalar architecture implements a form of parallelism called instruction level parallelism. So, here what you are doing, you are having a number of functional units, say in this case I have shown 4 functional units. What is being done, 4 different operations can be executed in parallel. That means, you will be identifying which instructions can be executed in parallel. So, it exploits instruction level parallelism, and by that all the 4 functional units can be kept busy by issuing opcodes for these 4 functional units. How it can be done, I shall explain. So, essentially within a single processors you are having multiple functional units, and where parallelism is exploited using the instruction level parallelism. And a superscalar processor executes more than one instructions during a single clock cycle by simultaneously dispatching multiple instructions to more than one functional units on the processors. As I have shown, there are multiple functional units, and in a superscalar CPU the dispatcher reads instructions from the memory and decides which ones can be run parallel. So, there is a special piece of hardware which reads the instructions from the memory and then identifies which operations or instructions can be executed in parallel, and this is all done by hardware. So, this is the schematic diagram how the Intel series of processors implement superscalar operation. So, you can see these are the x86 instructions which are complex in nature. As you know, those Intel series of processors are based on CISC. CISC stands for complex instruction set compute processor or computer. So, these complex instructions are received by a superscalar decode unit. So, superscalar decode unit will do the decoding and decompose a single complex instruction into multiple simple RISC like operations. So, that is being done by the decoding and translation unit. So, those complex instructions are translated into several micro operations which are typically simple operations like RISC operation, which are performed by RISC processors, reduced instruction set computer, and then they are sent to another piece of hardware known as dispatch unit. So, dispatch unit identifies which operations or micro operations can be executed, can be performed in parallel, and they are sent to these multiple functional units, and after the operations are performed by the multiple functional units, they are sent to another piece of hardware known as in order retire unit. So, what is happening here, you are fetching instructions sequentially one after the other, then you are doing decoding and sending it to the dispatch unit, but depending on the parallelism possible here, they may be executed with the help of functional units out of order. That means, in order fetching, those instructions which have been fetched in order may be executed out of order in this part of the hardware. So, you require another hardware which will ultimately reorder those instructions to get in order retire unit. So, you see you require power hungry decoder unit, translation unit, dispatch unit and then in order retire unit. So, these conventional superscalar out of order CPUs use hardware to create and dispatch micro operations that can be executed in parallel, and as the dispatch unit reorders the micro operations to keep the functional units busy, a separate hardware known as in order retire unit, as I have shown here, is necessary to effectively reconstruct the order of the original x86 instructions and ensure that they take effect in the proper order. That means, in this case we cannot really disturb the order. So, as the x86 instruction set is quite complex, as I have told, the decoding and dispatch hardware requires large quantities of power hungry transistors. That means, the functional units obviously will occupy some area, but this part of the hardware which will also require a very large portion of the processor. that means a large part of the silicon real estate will be occupied by these power hungry components. As a consequence, we have seen the Pentium chip has reached the power dissipation level of 100 watts, which we have already observed. Now, what is the other alternative? The other alternative is known as VLIW. VLIW stands for very large instruction word. So, in this very large instruction word approach, what is being done by hardware in superscalar architecture is performed by software. So, in this particular case, what is being done? The instructions are fetched from the memory, and then there is a kind of compiler. That compiler will do the necessary decoding, and then after decoding it will decompose complex instructions into micro operations. Then it will put several micro operations into a single instruction like this. Say a single instruction may have say 4 or 5 fields, and in each field will correspond to one simple micro operation. Say this is one operation, this is another operation, this is another operation, this is another operation. So, this is a single instruction of a VLIW, which stands for very large instruction word, very large instruction word. So, this why it is very large? Because you can see this instruction length can be much larger compared to a superscalar architecture. An instruction of a superscalar architecture can be 32 bit. On the other hand, this instruction, the width of this instruction can be 128 bit. That is why it is called very large instruction word, a single instruction word, because it comprises 4 different operations, and 4 different operations are here, and that is the reason why the width of these instructions will be longer than that of superscalar architecture. And what is the benefit that we are getting here? These after the after these superscalar VLIW compiler has performed conversion of the code into a VLI like instructions, then they can be stored in the memory and executed in order. So, in this case a compiler generates log instructions having multiple operations meant for different functional units. So, you see each of these operations, each of these instructions will be fetched one after the other, and then they will be executed serially, and you can see the operations corresponding to this add is going to this integer unit, this floating point add operation of code is going to the floating point unit, load operation code is going to the load store unit, and the BRCC this code branch code branch conditional code is going to the branch unit. So, in this particular case the CPU has got 4 functional units, integer unit, floating point unit, load store unit and branch unit, and which are fed parallelly by the codes available in a single instruction. So, here is a single 128 bit VLIW instruction is shown, and there this is fed to those operations. So, in this case what will happen, the implementation will be far simpler than that of superscalar architecture. One real real life example is the Crusoe processor. There is a manufacturer Transmeta. So, Transmeta has developed a processor known as Crusoe. So, the Crusoe processor is a very simple high performance VLIW processor with 2 integer units, 1 floating point unit, 1 memory unit and 1 branch unit. So, you can see 2 plus 3 plus 1 loads to 4 and 5 units. That means, the Crusoe processor has got 5 functional units inside the CPU, inside the single CPU, but the way it executes instructions is completely different from that of superscalar architecture. How it is done? You see the long instruction word, they call it in the transmitter jargon, it is called molecule. So, the long instruction word called molecule can be 64 or 128 bit. I have already shown the example of 128 bit long instruction, and those are and those 4, a molecule can contain up to 4 RISC like instructions called atoms. So, in the jargon of transmitter, each RISC like instruction is called atom, and then 4 atoms form a molecule, and all these atoms get executed in parallel, as you have seen, because each of them is fed to different functional units. So, they can be executed in parallel, and the molecules are executed in order. That means, these VLIW instructions are stored in the memory, and they are fetched one after the other, executed in order. So, there is no to convert out of order to in order with the help of a retire unit in this particular case. So, this particular you will get the details of this from transmitter's site, and the particular the part of this what I am discussing today is based on a based on this particular paper, the technology behind Crusoe processor, and this you can get from transmitter's site. Okay. And now, let us see what is the impact of this VLIW implementation. So, here we have made comparison of several processors, some of them are Pentium, which are in black color, this mobile Pentium 2, mobile Pentium 2, mobile Pentium 3, these are all Pentium processors, and you can see the process technology that have been used are given here 0.25 micron for mobile Pentium 2, mobile Pentium 3 0.25 micron, and mobile Pentium 3 0.18 micron. And then the on chip cache memory they have got is 32 kilobyte, and the on chip L2 cache they have is 256 kilobyte, and die size is 130 square millimeter for the first one, 180 square millimeter for the second one, and 106 square millimeter for the third one. On the other hand, Transmeta has developed 2 different types of cores. Initially, it was TM Transmeta 3120 implemented by using 0.22 micron technology, and here you can see they have used more on chip L2 cache, because the power hungry components which are present in those superscalar architecture is not present in transmitter processors. As a consequence, they can afford to provide more cache memory. So, this is the 36 kilobyte of cache memory is available in TM3120. Of course, it has no L2 on chip L2 cache memory, but the second generation processor TM5400 implemented by using 0.18 micron technology has got 128 kilobyte on chip L1 cache and 256 kilobyte on chip L2 cache. And in spite of using larger cache memory in transmitter processor, you can see the die size is much smaller. So, for the first generation processor it is 77 square millimeter. On the other hand, in the for the second generation processor, transmitter processor, the die size is only 73 square millimeter. So, we find that it is evident from the table that Crusoe processors using the same technology 0.18 micron, the comparable performance level and using comparable performance level requires about 50% chip area. So, chip area is much smaller. That means, with the same comparable performance the chip area requirement is 50%. Now, another very interesting demonstration is the the test of the pudding is in eating. You have to run some application to demonstrate the efficacy of the technique. So, here a Pentium 3 processor playing a DVD, that digital video it is executing, and the temperature is rising to 105 degree 5.5 degree centigrade. So, within the course here the temperature profile within the processor is shown. You can see in the central part the temperature is rising to 105.5 degree centigrade, and this kind of heat, this kind of temperature may lead to may lead to the point of failure. That means, the Pentium processor may fail whenever the temperature is rising to this level. Now, same applications whenever it is run on Crusoe processor, it is very cool. So, you can see the transmitter processor, the temperature is rising only to 48 degree centigrade. So, you do not really require any active cooling. So, in the Pentium processors you require active cooling, you require a very big heat sink, a fan on top of the heat sink, and like that. On the other hand, in case of your transmitter processor, no active cooling is required. So, normal ambient temperature is sufficient to cool it down, because the temperature is not much. So, this demonstrates the the efficacy of the approach proposed by transmitter. Essentially, it is a trade off between hardware and software. The hardware which is implemented in superscalar architecture to perform instruction decoding, instruction dispatching, then reordering, are being performed by a piece of software in transmitter processor by using VLIW architecture. Now, the most important component in this transmitter processor is a piece of software known as code morphing software. What it really does? The code morphing software mediates between x86 software and VLIW engine. So, essentially what it is doing, it is doing a kind of virtualization of the x86 processor. So, to the user it is nothing but a x86 processor. The users have written their programs in x86 code, but the there is a piece of software known as code morphing software, as it is shown. It is insulating the VLIW engine from the outside world. So, here you can see this the operating system, BIOS, and all the applications that you encounter in your traditional Pentium based systems. Those are all written in x86. That means, the Intel series of processors. So, you can have the traditional operating systems and also BIOS that is required there, and various applications that you use, word processing and various other things. And then these those codes are translated to VLIW code with the help of this code morphing software. So, code morphing software is essentially doing, it is fundamentally a dynamic translation system, a program that compiles instructions for instruction set architecture into instructions for another instruction set architecture. So, what it is doing, the code morphing software is translating codes of one instruction set architecture, that is your x86, to another instruction set architecture, that is your the transmitter's VLIW instruction set architecture. So, this code morphing software is the only program that is written directly for the VLIW processor. And as I have mentioned, code morphing software insulates x86 programs from the hardware engine's native instruction set. Now, you may be asking, if VLIW is so advantageous, why it has not been used earlier? The concept of VLIW, very large instruction word architecture, is existing for a long time, but it was not popular. The reason behind that is, when the task of writing code for VLIW processor is given to the user, it becomes a very difficult task. That means, user cannot handle the complexity of writing codes for VLIW architecture processors. But in this particular case, what is happening, that problem is overcome by this code morphing software, because the programmer or user is not is not bothered to write program for the VLIW processor. They are writing their programs in their traditional Intel processors, and the code morphing software is doing the necessary job of translation. And so, that is the reason why earlier VLIW processors were not that so popular. Now, the native instruction set can be changed arbitrarily without affecting the x86 software. Now, here the question is, suppose just like your Intel series of processors, it has gone from 386 to 486 to Pentium and so on. Instruction set has been, new instructions have been added, it has been made more and more complex. What about this Transmeta's Crusoe processor? It can be also changed. You can add more some important instructions in VLIW processors, but whenever you do such changes, what modification in your system is required. So, whenever you do that, only thing that has to be done is to change the code morphing software, nothing else is required, because in this particular system you can see the code morphing software is interfacing with the native VLIW engine, and if this engine is changed, only change that is required is in this code morphing software, and the outer layer softwares which are written in x86 need not be changed. So, user is not, it is transparent to the user, you can say, because the code morphing software is provided by Transmeta. Okay. Now, you may be curious to know how exactly this translation occurs. So, to illustrate that, I am illustrating that with the help of a very simple example. This is a piece of x86 code. Here you have got 4 instructions. First one is load data from stack, add to EX. So, you can see it is performing load operation and addition operation with the help of a single complex instruction. Then it is also, the second instruction is also doing the same thing. The third instruction is load from memory, and fourth instruction is subtract from a register. So, you can see these 4 instructions are consists of a code of a piece of x86 code. Now, the translation of this code into VLIW code is performed in 3 phases. In the first pass, that means the compiler, that dynamic translation unit operates in 3 phases or 3 passes, you can say. So, what are the 3 passes? In the first pass, the translator system decodes the x86 instructions and translates them into a simple sequence of atoms. In case of superscalar architecture, this is done by that decode and translate unit, it is done by hardware. So, here you can see it is done by the software. So, these 4 instructions are now decomposed, are now converted into simpler sequence of operations, and they call it atoms. So, you can see load from stack, one instruction, add another instruction, load another instruction, add another instruction, load another instruction, subtract another instruction. These are the, so this is done in the first pass. So, after this first pass is over, in the second pass, the translator performs typical compiler optimizations such as common subexpression elimination, dead code elimination, and so on. So, whenever you are writing a optimizing compiler, you have to do different types of optimizations, and the optimizations like dead code elimination. Some codes are generated by the compiler which are never executed. So, those codes can be removed, and common sub expression eliminations, same computation you have done maybe n times or 4 times, only one computation is sufficient. Those things can be removed with the help of a optimizing compiler, and I have given 2 such examples. There are several such optimizations which are performed by optimizing compilers. So, in the second pass, those optimizations are done. So, in this particular case, essentially we have seen one instruction. In the previous case, we have seen 1, 2, 3, 4, 5, 6 codes, 6 instructions were there, which have been converted into I mean 1, 2, 3, 4, 5. 1 has been removed, because we have seen in the previous case you are loading to a temporary register 30 and you are loading the same data to another register 31. So, which can be eliminated, because you can reuse the value twice. So, you can reuse, you are loading it into this temporary register, then you are reusing it twice, and so one instruction can be removed. So, that you have removed a dead code which is not required, and then load and subtract. So, this is how you have performed some kind of optimizations. Then you will do a third pass, and that is the final pass. The scheduler reorders the atoms and groups them into individual molecules, which is somewhat similar to the function of dispatch hardware. We have seen in a superscalar architecture, after the complex codes have been converted into micro operations, they are sent to multiple functional units with the help of a dispatcher. So, here again it is done by software. So, in the final pass, the scheduler reorders the atoms and groups them into individual molecules, and which is somewhat similar to the function of dispatch hardware, as I have told. So, you can see these 5 operations are now packed in a fewer number of VLIW instructions. So, you can see we have it has been possible to pack 2 operations. Of course, you have to see which operations can be executed in parallel. It may not be possible to execute all of them in parallel. So, whenever the whenever you put them in a single VLIW code, then you have to see which operations can be executed in parallel. For example, this load operation and this particular instruction, these two can be executed in parallel, but not the other two, because unless load is done, you cannot perform an addition operation, and neither you can perform load operation. So, only these 2 codes can be executed with the help of a single VLIW instructions. Then the remaining 3 are performed are put in a single VLIW instructions, and they can be executed in parallel. So, now this can be stored in the memory, and then they can be fetched one after the other. So, the first this particular VLIW instruction will be fetched, and all these atoms will be executed together, and then the second instructions will be fetched. I mean the order, it will be done in the same order, then all these 3 atoms will be executed in parallel. So, this is how the program execution take place in VLIW architecture. So, the program is executed in order by the hardware, and the molecules explicitly encode the instruction level parallelism. That means both superscalar architecture and VLIW architecture are exploiting instruction level parallelism, but they are exploiting instruction level parallelism in 2 different ways. One is doing by using hardware, another is doing by using software. Okay. Now, here is a comparison between superscalar and VLIW processors. So, you can see what happens in case of superscalar architecture. Instructions are fetched from memory and decoded them into micro operations, which are then recorded by a out of order reorder. It will be reordered by a out of order dispatch hardware and fed to the functional units for parallel execution. And the out of order dispatch unit has to translate and schedule instructions every time these are executed, and it must be done very quickly. So, we have seen whenever you are executing a program, say you are executing 10 times, this decoding, dispatching, reordering have to be done 10 times. Every time you execute, all these things have to be done 10 times, and obviously 10 times power dissipation will take place. And so, power dissipation takes place each time the program is executed. Now, what happens in case of VLIW processor? In VLIW processor, the code morphing software CMS translates an entire group of x86 code instructions once and saves the resulting translation in a translation cache memory, and in subsequent and use them in subsequent executions. So, what is happening here, in case of VLIW processor, once the translation has been done by the code morphing software, you can store them in cache memory, and you can executing them many times, maybe 10 times, 100 times depending on the application, but each time you do not have to do the translation. You will do the translation only once and execute them as many times as it is necessary by the application. And what happens in this case, the cost of translation is amortized in code morphing approach over many executions. That means, obviously the translation operation done by the code morphing software has some overhead. That overhead cost is amortized over a large number of executions. So, as a consequence, what is happening? Power dissipation is much less, as has been demonstrated by that video execution examples. Okay. So, this is the comparison, and obviously apart from using the basic concept of VLIW architecture, doing translation by using software, some more additional, you require additional techniques to improve the efficiency of this particular processor architecture. Number one is caching. What is caching? In real life applications, it is very common to execute a block of code many times over and over after it has been translated once. You do that in real life, that executable code you save in a memory. So, here also you will be saving, but where you will be saving? You will be saving in a special type of memory known as translation code, and it operates like a kind of cache memory. You may be familiar with cache memory. What is the task of a cache memory? To execute a program, what is the primary requirement? Primary requirement is that it must be present in the main memory. Now, instead of storing it main memory, a part of the program is stored in the cache memory. Which part? That part which is executed quite often. We use a property known as locality of reference, and by using the locality of reference, a part of the program which is executed most of the time is stored in the cache memory, and that is the concept used here. In this case, a separate memory space is used to store the translation cache and the code morphing software. That means, maybe you have got say 100 different applications, but all of them you may not be executing quite often. So, which are executed quite often, they are those codes you will be storing in the in this particular cache memory, and obviously you will be doing it by using the locality of reference property. So, it allows reuse the translated code by making the use of locality of reference property. So, caching translations provide excellent opportunity of reuse in many real life applications. So, this is very quite common in real life applications. Apart from caching, another technique which is also used to improve the performance, which is known as filtering. What do you really mean by filtering? It is common knowledge that a small percentage of the code accounts for 95% of the execution time. Suppose you have written a big code, and it has been observed that only 10% of the code is executed 95% of the time. So, maybe a loop, the code which is part of a loop, that will be executed many times. Other parts of the code may not be executed as many times. So, what can be done? You can focus on that part of the code which is executed many times. Rather, you can do more optimization, you can devote more time for optimization on that part of the code. So, you can selectively devote shorter or longer time for optimization to different parts of the code, that is filtering. So, this opens up the possibility of applying different amounts of translation efforts, that is the efforts for optimization to different portions of a program. The code morphing software has built-in feature of wide choice of execution modes of x86 code, starting from interpretation, which has no translation overhead at all, but the execution is slower, to highly optimized code, that means some part of the code has to be highly optimized, which has large overhead for code generation. That means that code morphing software will devote long time for to optimize it, but that runs first at once translated, because that will be executed many times. So, a set of sophisticated heuristics helps to choose from several execution modes based on dynamic feedback information gathered during actual execution of the code. So, what is being done, you know, a particular program you may be running many times. So, whenever it is run once, the code morphing software gathers information, which part of the code is executed quite often, which part of the code is executed less often. So, based on that, you know, the translation effort is done differently for different parts of the code. So, this kind of filtering is done. Then another important thing that is being done is prediction and path selection. So, the code morphing software can gather feedback information about the x86 program with the help of additional code present in the translator, whose sole purpose is to collect information about block execution frequencies or branch history. You know, here what is being done, a kind of branch prediction is done. So, branch prediction is done why? For example, here there is a branch, it may be taken, in that case it will go in this direction, and if the condition is not satisfied, it will go back to this. So, if the taken probability is more, then you will put more effort to optimize this part of the code. On the other hand, if the untaken probability is more, you will put more effort to on this part. So, depending on how often a piece of x86 code is executed or whether conditional branch instruction is balanced. So, if 50% probability, then of course, there is no bias in any particular direction. So, or biased in a particular direction, decision can be made about how much effort to put to optimize that code. So, whether you will put more effort to this code or this code, that is decided by this prediction and path selection. So, in a conventional hardware only x86 implementation, it would be extremely difficult to make similar kind of decisions. That means, whenever you are doing it by hardware, it is not really possible to devote more time for optimization to a particular part of code, less time for optimization to another part of the code. This is feasible only because you are doing by software. Okay. Here is a more complex example. So, you can see these are all a complex x86 instructions, which is converted by the code morphing software into only 10 instructions. Of course, if you look at a particular molecule, you will see that all the fields are not filled up, all the atoms are not present, that will happen. So, you cannot expect to have complete parallelism or 100% efficiency, okay. But in spite of that, it will give better result. So, with this we have come to the end of today's lecture. So, we have discussed a very important step known as hardware software trade off, which can be used to reduce power dissipation, particularly which will minimize the switched capacitance of a circuit. Thank you. In the next lecture, we shall discuss about other techniques.